Okay, so in looking at reactions in gases, there's a special thing that we can do. And so I'm going to call this gas reactions. And let's look at an example and explain it as we go. So in this case, I have 5 liters of propane gas. Propane gas is C3H8. And then I say it's burned. As soon as I see it's burned, I know I'm adding oxygen and I'm getting smoke. CO2 plus H2O, water. And then it's asking me what volume of gas was produced. So the values that I know is I have 5 liters of propane gas, what volume of CO2. Okay. There's a trick to this, and I want to explain that trick. So first let's do the trick. I know I start out with 5 liters of propane gas. Oxygen's a gas, carbon dioxide's a gas, and water is actually going to be in gaseous form when we burn it. Okay, so all of these are gases. If they're already all gases, I don't need to do much with the volume because the volume is going to follow the mole ratio. So first I have to find the mole ratio. You find that by balancing your equation. So let's quickly balance our equation. I have 3 carbons on this side, so I need 3 over here. I have oxygen in too many places, so let's move to the hydrogens. I have 4 there, which means I need, 8 here, which means I need 4 here. That gives me on this side 3 times 2, 6, plus 10 oxygens, 2, so 5. So it's a 1 to 5 to 3 to 4 ratio. Now, that's our mole ratio. The mole ratio is going to match with our volume ratio. And I'll show why in a second, but all I need to do, if I want to know the volume of how much oxygen was made, it's going to be 1 times 5. So for every one of these, there's 5 of these. For every 5 liters here, 5 times 5 is the 25 liters of oxygen gas is needed. If I want to know how much CO2, it's 5 times 3. It was 15 liters of CO2 gas was produced. By the way, that was the answer we're looking for. And if I want to do this, it'd be 20 liters of water, vapor, or gas that's being produced. Now, why does this work? It's real simple. Our ideal gas law, PV equals nRT. And so what we see is there is a relationship between volume and moles. In this case, the pressure is held the same. So we can adapt this formula to look at various things or even comparisons. But when you look at it, so there's 5 liters for a certain number of moles. So in this case, it's 5 liters for 1 mole of stuff. Well, if it's at the same pressure, the same rate, and same temperature, I can have a different gas that's now in a mole ratio, and so this is going to be 3 moles. Well, what would that ratio be? It follows this standard ratio, so this is why this is 15 liters. Okay, if you want to solve it more, you could isolate and essentially say that pressure over RT times volume is equal to N. These are just constant for my entire equation, and so when I compare N of C3H8 to the N of CO2, and the mole ratio of this is going to be, there's 1 mole of C3H8 for every 3 moles of CO2. Okay, if that's the case, I then now can simply exchange the mole aspect of this, the N part, with the V's. And so substituting that in, I just multiply it out and I get my answers. So it's only if these are gases. This doesn't work, it has to be a solid, and has to do with the fact that the solids don't have pressure. If you look at a container, the gas is easily spread out. If you look at a solid, the solid's going to be in a chunk somewhere in it. Okay, even a liquid doesn't fully fill the container properly, so this only works with gases. And it's our special gas reaction. So I don't have to do any of this extra math. I just need the volume of one gas and a balanced equation, and I can find the volume of all the other gases. Pretty easy, huh? Okay, good luck.